Hi physics students, this is Mr. Gloria coming at you again. So let's talk a little bit about the ways to express or discuss motion. So we really have three different techniques that we've kind of studied to discuss objects that are moving. We're talking about linear one-dimensional motion, kinematics. No two-dimensional motion at this point yet, no free fall either. So we have our motion graphs, and we said really there were three types. Position time, which we can label xt, velocity time, acceleration time. These are our motion graphs. And by looking at different shapes and different things about the graphs, for example, slopes, tangent lines, areas, we can determine from maybe one graph, we can determine the other two. We can also determine kind of what's happening with the object in motion. We've also talked about different types of equations, and I've kind of labeled them how far, how fast, and the combination equation. So our main equations then, our main equations, let me get that sheet over here. We've got our constant velocity equation. That's an object that's not accelerating. We have our what I call our how far equation, our how fast equation. I've kind of labeled our accelerations as getting faster, would be a positive constant acceleration. Minus CA would be an object getting slower. And then we also developed then what I call the timeless or combination equation. We took these two equations and we kind of merged them together, and we factored out the time. And this is really helpful if we don't know the time that something is in motion. We also have our verbal statements, words. So in today's discussion we really want to focus in on using verbal statements and motion graphs to qualitatively talk about different scenarios that we can have with cars or other objects that move. And what I mean by qualitative is we really don't care about the numbers, we just care really about the discussion and the shapes. Let's take our first example, and I'm going to go to my dot camera here shortly. So let's say we have an object that's moving away from a reference point. That reference point could be home, it could be a stoplight, it's just a place where we're starting our stopwatch. Maybe we have this car moving away from a reference point getting faster. That car starts from rest, moving faster and faster. And finally there's a point in time that the driver will activate his or her cruise control. So let's go ahead and start this sort of scenario here. So we have, let me grab a pen here. So we have maybe a car that starts from rest. It gets faster. So that would tell us then we're having an acceleration. And it starts from like a reference point. So starting from rest means our initial velocity is 0. And it starts from a reference point. That means our initial position is 0. So again, let's just deal with this qualitatively really. So let's just I'm just going to kind of put down our three different graphs here. So we have our position time, our velocity time, and our acceleration time. And maybe you only use kind of a highlighter here. Sometimes it's easier for me, I like to start maybe with the velocity graph. And so if the object has a positive constant acceleration and it starts from a VI of 0, we know it's got to start at this point here. And again, we're not really sure what that value is for the velocity. Again, we're just looking at qualitative types of graphs. So we would have a diagonal line here, right? Now, what about basically that diagonal line is kind of an important idea. Well, the slope is, right? The slope is the acceleration. So that slope is going to stay constant. So that means we need on our AT graph, we need a horizontal line in the first quadrant. Now, as we discussed in class earlier, if we look then at areas, the areas will tell us the displacement. And for this object here, we know then that we're going to have kind of a parabola, all right? Because we're based on a triangle, 1/2 base times the height, and that comes out to be 1/2 AT squared. Now, the important thing on a position time graph is we can look at tangent lines, and that can kind of help us. So our first tangent line then would be a horizontal. That's telling us an initial velocity of 0, and our velocity then increases. Our slopes of our tangent lines go up. Okay, so we basically have our graph for the object getting faster. And maybe there's some point in time then that the driver puts on the cruise control. So then we have our constant velocity. So basically after this happens, we have CV. Well, what would our position time graph look for CV? Well, for CV then we have a diagonal on our position time graph. So we're going to take that last tangent line and we'll just kind of extend it as a diagonal. Okay, so now we got really a piecewise function here. We've got then getting faster and then staying at a constant velocity. Well, what would that look like then with my velocity time graph? Well, because my velocity is not changing, I will now then have a horizontal line here. What about my AT graph? Well, I know we really can't have an instantaneous transition there, so we often show on the AT graph kind of like a dotted dashed line there. So at some time we're really having an instantaneous change there. We're going from getting faster to staying at that same speed. So then our acceleration would be 0. So we would have something that looks like this. So the combination of these graphs then are telling us that the car starts from rest, okay, initial velocity of 0, starts at a reference point, initial x sub I is 0, the object is getting faster, okay, there's our parabola, and then the object stays at a constant velocity. Okay, in the first scenario, I basically gave you the verbal statement and we came up with our graphs. Sometimes we have one of our graphs and we need to create maybe the other two graphs and then also create a verbal statement. So let's say we have maybe a car that's doing something like this. So let's go with our VT graph. Let's say we have something that kind of looks like that. So what does that really imply to us? What information can we get from the VT graph? Well, it looks like at our initial time that the object is moving at a constant velocity because we have the horizontal line here, so this would be CV, right? And then the car at some point in time, the car then is slowing down, and the car slows down to rest or to a final velocity of 0. So this would imply then a minus CA. Okay, so initially then on my acceleration time graph, we're not going to have any acceleration, right? Then our acceleration, or our slope here, is negative. So we're going to have a negative, then we'll have a transition here. We'll have a negative, then acceleration. There's my AT graph. Now we know then for CV that we're going to have a diagonal line. And let's say the car is starting from a reference point. So the car at that reference point is moving with maybe its cruise control on. So we would have then a diagonal line. and then the car is going to slow down. So we'll have then a bottom opening parabola, something along those lines. Again, we can use our tangent lines. We can use our tangent lines to really reflect what we're seeing with our velocity time graph. So that last tangent line then represents the car at rest. So our velocity is getting smaller and smaller with respect to time. So we can translate all that information really into a verbal statement, right? So the car started from a reference point with some constant velocity, okay? And at some point in time then the car slowed down. And eventually the car came to rest. So we could translate kind of all that into a sentence or two and talk about a verbal statement. Maybe do a third scenario here. So in this case, let's start with our acceleration time graph. Let's say we have something that kind of looks like this. I don't know if you can kind of see that there, but what we have is we're starting off with the zero acceleration, and then we have some sort of a positive acceleration, and then we're back down to zero acceleration. Now with that first zero acceleration, we're really kind of not sure. We need a little bit more information, right? The car could rest, or the car could be moving at some sort of non-zero constant velocity. In both cases really we have CV, right? If the car's at rest, our velocity is zero. If the car is moving with some constant velocity that's not zero, then maybe we have the cruise control on. So let's say we have that sort of scenario. So maybe this driver is driving at some sort of a velocity, constant velocity, and he or she then passes a car on the road, needs to accelerate, and then reactivates the cruise control at some higher value. So in this case, maybe we would have then on our VT graph, we would have some sort of a constant velocity, non-zero. That kind of represents that part of the AT. And then we would have a positive diagonal here. Okay, there's the car accelerating. And then at that higher velocity, the driver then activates the cruise control. And we might then go back to something like this. So we have a CV here and a CV there and an acceleration there. We have a positive slope there that matches our acceleration there. So what sort of position time would we have? Well, for that CV, again, if we're starting at a reference point, that CV is going to be a diagonal. And then we're going to have a parabola. Kind of hard to see that. And then we're going to have another diagonal. Again, these diagonals here really, this second diagonal should kind of be connected with the tangent line, that final tangent line of that parabola. So if we look at our parabola, we're going to start with a pretty high velocity and get a little higher. Okay, so if we created a verbal statement here, our car has some sort of a constant velocity. It accelerates, okay, to some higher value, and then it reaches a new sort of constant velocity. That I have for you. In this case, let's start with our position time graph. It may be kind of hard to see exactly what's going on here, but we have a diagonal line, and that diagonal line starts at a reference point. Then we kind of have this bottom opening parabola. Then we have a horizontal line, and then we kind of have a top opening parabola. So what is that really saying to us here? Well, the object is going to start with having a diagonal, so we're going to have a constant velocity to start. We're going to start off with a horizontal on our VT. The object then is going to get slower. It's going to come to a rest or stop. So our tangent lines here show us that the car eventually then stops at this time, at this specific point in time. So we're going to have a negative diagonal. Okay, then the car stopped for a while. Okay, we're not changing any position here, so the car is going to be stopped for a while. And then the car basically then has this top opening parabola, so the car is getting faster and faster. So we have then this positive diagonal there. So this would tell us here that the acceleration initially is 0, or at some sort of a constant velocity. Okay, then we have a negative slope, so our acceleration here would be negative. There's my transition. My car then has stopped, so my acceleration's back to 0. And then my car has a positive acceleration. Okay, again, we can kind of put everything in a verbal statement. The car's traveling at some sort of constant velocity. The car then slows down. Okay, this first constant velocity is not 0. And then the car then has a constant velocity of 0. And then the car is going to be getting faster and faster at the end. Okay, here I have a fifth scenario, and this is kind of something we haven't really discussed before, really, this kind of scenario, but sometimes we can, again, the idea is to use our clues from our graphs to come up with kind of what's happening here. So in this case, we have a diagonal line here. So I kind of created a diagonal line. We have an object really that's away from a reference point that's coming back towards a reference point. So maybe, so this is traveling at some sort of a negative velocity, right? But it's constant. And so at some point then in time, we kind of see then this sort of shape or a parabola. And if we use our tangent lines here, the object eventually then comes to rest, but these are basically negative tangent lines, right? So they're negative velocities, but that negative velocity is getting slower and slower, or getting less and less. So this represents a car at some velocity, and maybe, or some object, and maybe that car then is coasting. And that car gets back to kind of its reference point and gets slower and slower. So this really does also represent an object getting slower, but it's an object getting slower going back towards a reference point. So how would we kind of convert that into a VT and an AT? Well, we have a negative constant velocity. Do it in another color. Okay, negative constant velocity. We know that velocity eventually will get to 0. But that velocity is going to stay at some sort of a negative value, but it's going to get smaller and smaller. See, I'm trying to draw those little V's are really tiny there. And so we have something then that kind of looks like this. Now this is again something a little bit different. So we have a constant velocity here that's negative. And that constant velocity gets slower and slower. Now this really represents an acceleration, right? A positive acceleration. So in the first bit of time, we have no acceleration. And then we have a positive acceleration. So depending on the scenario, our acceleration may be positive. It could be an object getting faster. Well, in this case, the object's going back towards a reference point. So, and the object is actually getting slower, but it's a positive acceleration. So putting that all in kind of a verbal statement, an object is not at a reference point. It's coming back towards a reference point. It's moving at some sort of sort of velocity back towards the reference point, so that would be kind of a minus CV. Okay, there's some point in time that it gets slower, right? It's getting slower and slower, and finally it comes to a stop. So that's really kind of, you can call that then a positive acceleration, but it's a positive acceleration going back towards a reference point, so the object's getting slower and slower. It's kind of a complicated example. One of the key things that can always really help you on some of these more complicated or confusing examples is to use tangent lines to kind of help. Again, the tangent lines, the slope of these tangent lines really reflecting how fast the object is moving at that instant, instantaneous velocity. Okay, let's maybe look at another scenario. Let's again start with a position time graph. So let's draw our position time graph, our VT graph, and our AT graph. Let's have another one. Let's give another one to the position time graph, and let's say we're doing something like this. Okay, so let's say we have a position time graph that kind of looks like this. So what is that really telling us? So we've got then an object that's starting away from a reference point that's coming back towards the reference point, right? So this is again a slope. It's a diagonal, so that's telling us that we're going to have a constant velocity. So that's going to be a negative velocity because we're coming back towards a reference point. We could kind of also picture this maybe like a number line, and this being our reference point. And so on a position like time graph, we'd be traveling at a constant velocity back towards that reference point. Okay, we get to that reference point, right, because this is our zero axis. We're going to stop for a while. Okay, so we're at rest, so our velocity here is 0. Okay, so we're going to rest for some time. So let's start creating our velocity time graph there. So we would have a negative velocity. Okay, then our velocity would be 0 for some time. We know we really can't make these transitions instantly, but we can show those transitions as dotted lines. And then we're going away from a reference point. But it looks like this velocity is less inclined, so maybe we're going a little bit slower. But that's going to be a constant value too. So something looks a little bit like that. So what would our AT graph? Well, in all of these cases, really, we're not accelerating. We're traveling at constant velocity, negative, at 0, or positive. So our AT graph would be 0. All right, throughout that time. Okay, kids, let's do just one more example here. Let's give you a kind of a common scenario for maybe drivers. Maybe you're along some sort of a street that's got several stoplights. Maybe you're stopped kind of at a stoplight. That stoplight turns green and you accelerate. You get faster and faster. Maybe you hit some sort of a velocity. You stay constant for a while. And then you see up ahead that the next stoplight's red, so you slow down to a stop. You know, this is a pretty common scenario. In fact, we're going to be building a project in class called a pullback car that kind of operates on that scenario, and it's a pretty common scenario for drivers. So let's create our graphs here. So we have our position time, our velocity time, and then our acceleration time. So again, the scenario is kind of like this verbally. We have an object at rest. It gets faster and faster for some amount of time. It maybe hits a constant velocity. Up ahead we have a red light, so the driver slows down back to rest. So you want to start with the VT graph first. Okay, we're starting at some sort of a constant velocity. We're getting faster and faster. We then stay constant maybe for a little bit, and then we get slower and slower. We finally come back down to a stop, something like that. So that's kind of that scenario as a VT graph. It's kind of like a pullback car, you know, when we pull the car back, it accelerates, it gets faster and faster. then it stays maybe constant for a little bit, and then it gets slower and slower, and finally it comes back down to a stop. Okay, in terms of the AT graph, we would have a positive acceleration followed by 0. That's that. And then we would have a negative acceleration. Okay, so our velocity is changing, so we've got to show that with our tangent lines. We're going to have a parabola here. We're going to have a parabola of some sort there. And here then we'll have some sort of a diagonal, right? So our velocity is getting faster. Let's say we start at a reference point. So our velocity is getting faster, but it starts at 0. So there's kind of our parabola. Okay, if you show that tangent lines, it'd be getting faster. Okay, we're going to maintain a constant velocity for some time. There's your diagonal. So we're getting faster here. And then we have our diagonal here. And then we have an object that's getting slower. So there's our getting slower parabola. Again, we can kind of show all those with our tangent lines. Our tangent lines are getting larger here, or slopes of our tangent lines. We reach in a constant velocity, and then our tangent lines get smaller and smaller, and finally, there's a point then that my last tangent line's horizontal. That means the slope is 0, and my instantaneous velocity at that point is 0. So again, these points, these transitions here, these points correspond to these same points on the position time graph or on our acceleration time graph. Hey, we'll talk to you later, kids. Bye.